This is still actually being recorded. I could upload it like this. Hello, George Romanic here. Today we are starting a playlist on kinetic theory of gases. Immediately after this series of videos, we will continue with thermodynamics and then application of thermodynamics to atmospheric sciences as well as engineering. Thermodynamics and kinetic theory of gases are crucial theories and concepts in proper understanding of fluids such as air. Of course, therefore, this is very, very important, crucial in atmospheric sciences. Now, quite often people just define equation of state for ideal gas and continue with thermodynamics, but I think there are many, many subtleties that deserve to be addressed before we arrive at equation of state. And these subtleties are something that seems obvious to many people, such as what is pressure to begin with, what is temperature, how did people manage to define these bulk properties of a gas. This is what we will address in next several videos, and you will see from these videos how naturally we derive equation of state for an ideal gas. What is an ideal gas? Well, that is a gas where molecules and atoms are represented as perfectly solid, indestructible balls, little spheres that are bouncing around, hitting each other, hitting the walls of the container, and these collisions are perfectly elastic. And perfectly elastic means there is no loss of kinetic energy when two particles collide. I will shortly describe that more quantitatively, but that's the premise of an ideal gas. Of course, air is not perfectly ideal gas, but if you stay with me in this series of videos, you will see how this assumption of an ideal gas to the air is so good, and there are so many, pretty much all, not absolutely all, but almost all properties of a gas such as air that can be described using ideal gas law and kinetic theory of gases. Why was kinetic theory of gases invented to begin with? Why did Maxwell, Boltzmann, Gay-Lussac, Avogadro, and so on, many people, why did they work on this? Well, over the course of the time, it became obvious that matter, and here we are concerned primarily with gases, are made up of small particles, molecules, and atoms. Of course, atoms bound together to make molecules, so throughout this series of videos I will use molecules, atoms interchangeably. And it was also obvious that there are so many of these particles. For example, in the room where I'm sitting, there are trillions and trillions of atoms in the air, and I know because I calculated it. And I calculated it, as you will see in a few videos from now, using the principles of kinetic theory of gases. So how do we represent trillions and trillions of atoms? It's impossible to track each atom, what it is doing, how it is colliding with other trillions minus one atoms, how it is colliding with the walls, and so on. So people developed statistical theories. They, of course, require some assumptions, which we will address today, but these assumptions are so good that kinetic theory of gases is very, very applicable to gases at pressures and temperatures that we experience around us. So now, without any further ado, let's talk more quantitatively about kinetic theory of gases and the main assumptions and postulates in this theory. Let's say we start by having some gas, which is basically a lot of particles. And these particles, which are atoms or molecules, can be, let's say, in a box, but they don't have to be in a box. Now, even outside of the box, there are some particles usually. So the question is, how do we represent the behavior of this gas without looking into every single particle and what that particle is doing? Of course, even if we wanted to investigate the behavior of every atom in this gas, it would be impossible. In my room, there are more than trillion atoms of air. I calculated it, and a few videos from now you will see how I calculated it. But the point is, it would take forever, the age of the universe, to calculate the position and velocity of each particle just in my room. Now, all these particles are moving around, bouncing. Let's say maybe this one is bouncing into the wall and then going away. This one will collide with that one. So all these particles are constantly interacting with each other and the container. Kinetic theory of gases was developed to give us statistical representation of the behavior of this gas. And that statistical representation relies on the main three properties of the gas. And that is pressure, temperature, and volume. Now, volume should be intuitive to you. That's basically an amount of space enclosed in a surface, and that surface can be a real surface, like this container, or imaginary surface, which we often use in atmospheric sciences. We say an imaginary parcel of air. So we really mean, imagine there is a surface that is enclosing a parcel of air of some arbitrary shape, and then we look into particles that are inside, but there is no real surface. At any rate, that's volume. Temperature and pressure, I will leave them from this video, because I will have videos specifically defining temperature and pressure in terms of kinetic theory of gases, because these quantities are not as intuitive as you might think at first glance. Now, if we go back to look into the behavior of this gas, it is important, of course, to realize that these particles are really atoms or molecules. Now, molecules are a collection of atoms held by electrical forces, so for the purpose of kinetic theory of gases, it is not really important whether these are molecules or atoms, and I will probably interchangeably use both these terms. Now, if we zoom in, let's say we zoom in into this particle over here. Perhaps that particle is atom of helium. Okay? So this is zoom in of that particle. If this was helium, then we would see that it has two protons in the nucleus of that atom, and there are also two neutrons. Protons are positively charged particles, subatomic particles, and neutrons don't carry electrical charge. And somewhere in the orbit around this helium, there are also two electrons. Now, people studying quantum physics, they are looking at this picture and say, you cannot draw orbit for an electron in a classical way. And I know that too, but neither I nor them know how to do it better. So, for now, I will just say electrons are orbiting nucleus. Now, let's look into this particle over here. If we zoom in into this guy over here, perhaps this is hydrogen. Hydrogen is the simplest atom. It only has one proton and electron somewhere in the orbit. Now, if these two atoms are together, there will be some electrical forces of repulsion if these two electrons are close to each other, or depending on the orientation and all other properties, there can be even attractive forces, because this electron might be attracted to this positive core. However, this is now very important, in the context of kinetic theory of gases, these two particles, as well as their interaction, are not represented in an atomic way, but we say this particle is simply a three-dimensional sphere, a ball, and this particle is also a three-dimensional sphere, a small ball. They don't have any internal structure like protons, neutrons, electrons, whatnot. We just say they are spheres. Instead of electrical interaction between these two atoms, we say if these two balls collide, they collide collide like billiard balls over here, let's say, and they just bounce off. All these particles inside of this container are bouncing off the wall of the container and they are colliding with each other. And these collisions are perfectly elastic. And this is definition of an ideal gas. What does it mean that collisions are perfectly elastic? Well, let's say if these two balls are colliding, perfectly elastic collision means that kinetic energy is conserved. So that is another assumption of ideal gas law, that collisions are perfectly elastic. Next assumption is that these particles in the container are much smaller than the container itself. So if we take all these particles and we sum their volumes, that volume is negligible compared to the volume of the container. So quite often people would say that means that these balls are point-like spheres because they are so small that all of them together are much smaller than this container. That also consequently means that the distance between particles is much larger than the size of the particles. So if this is one particle and this is another particle, you can see that in this case their distance, let's say capital D, is much larger than, let's say, diameter of this basically point-like particle. Now, within kinetic theory of gases, these two particles can have different masses. This can be mass m1, this can be mass m2, that is fine. Kinetic theory of gases can handle that. Now, another important information related to kinetic theory of gases is that, as I mentioned earlier, this is statistical theory of the behavior of the gas. And statistical theory means that we really have to have a large enough sample that will represent properly the behavior of the gas. Now, how do we quantify that phrase, large enough sample? Well, let me try to do it in the following way. Let's say all these are particles in some container, and you will see why I am putting a lot of them. Now, let's say I want to statistically investigate the behavior of this gas. And I take a volume, okay? Now, let's say that this over here, this window, represents surface of a volume. If this volume is here, there is a lot of particles over here. But then if I move this volume over here, same volume has only two particles. Even if I place it properly, there is no particles in the volume whatsoever. Here, maybe one particle. Here, there are certain number of particles. Look, as I am moving this volume around, this is important what I will say now. As I am moving volume around, I am picking up small random fluctuations in the gas. A lot of gas over here, a lot of particles, it just happened, random fluctuation. Nothing over here. It can happen. Now, this also works in terms of time. In other words, if I have a lot of fluctuations over here and I leave volume, well, I mean, these particles will leave the volume, some other particles will come into the volume, and maybe much less will come in than what leaves, and you will end up with not that many particles in the same volume. Conclusion here is, if you have very small volume, then number of particles is too small to be representative for the entire volume of the gas in that container. What you need to do is, instead of this small volume, take bigger volume. You see, now if you have bigger volume, for example, in this case, these high fluctuations over here kind of average with absence of gas over here, and pretty much over here you have an average number of atoms. So this is more representative than the previous size of the volume. So conclusion, of course, is the bigger the volume, the better you are representing the statistical behavior of this gas. Now, at some point, the volume will become so large that all, let's call it, negative fluctuations and positive fluctuations will cancel out. And that size of the volume is called thermodynamic limit. So, kinetic theory of gases works only once we reach or exceed thermodynamic limit. Below that, you're picking up small fluctuations in the gas, and that's not good. Once you reach thermodynamic limit, as you increase volume, you are linearly increasing number of particles in that volume because all positive and negative fluctuations simply cancel out. Which, as you saw, for the small volume is not the case. This is high fluctuation, nothing is cancelling it out. This is small fluctuation, nothing is cancelling it out. This was the introductory video to kinetic theory of gases. After this video, the things get serious. Some of the next videos will become very, very mathematical. A lot of derivations, beautiful mathematics. Some of the videos will be experimental. We'll do amazing experiments, and you will see the applications of statistical theory such as kinetic theory of gases in front of your eyes. Until next video, goodbye.